Problem 3 will be different from the previous two problems. For this problem, we will have infinitely long wire with current, constant current I node flowing in this wire. And we will have a frame with two resistors. This rod that can move has resistance R1, and this is resistor with resistance R2. They are connected by a resistance-free wires. So this dimension is given, this dimension is given. I'm moving this rod with constant velocity v to the left. And what we want to find current flowing through the resistor R2 if self-inductance is ignored. Law. Which law will we use? Well, we will use Faraday's law to solve this problem. And according to Faraday's law, integral E dot dr along closed path is equal to minus time derivative of flux of the magnetic field, B dot ds. So this is flux, we call it phi, and phi is integral B dot ds. The first question that we need to ask ourselves is why there will be induced current. First of all, is there a magnetic field? Yes, there is magnetic field created by this current I node in this wire. What is the magnitude of the magnetic field, of this magnetic field? We need to use Ampere's law to figure it out. According to Ampere's law, integral B dot dr is equal to mu node current enclosed by this loop. So my loop looks like this. Then I have B times 2 pi r. We did it many times. B is parallel to each point of this dr. I simplify the left-hand side of Ampere's law, and this is equal to mu node, and current enclosed is I node. So now we know the magnetic field, the magnitude of the magnetic field. The magnitude of the magnetic field is mu node I node divided by 2 pi r, where r is distance from this wire to the point where I'm looking for the magnetic field. What will be the direction of the magnetic field? You need to use your right hand to figure out the direction of the magnetic field. Ironically, I use my left hand because you see my mirrored image. I put my fingers along the current, and here below this wire, my fingers go out of the page. And above the wire, my fingers go into the page. So the direction of the lines of the magnetic field here below is out, and above is in. We are not interested in this area, but we are interested in the magnetic field created in this area where we have our circuit. So the direction of the magnetic field in the area that we are interested in is out, and the magnitude is right here. Okay, so there is magnetic field, but this magnetic field does not depend on time. So where is time-dependent process that we need? Well, we move this rod. Since we move this rod, then area changes, area bounded by our path, by our circuit. Area changes. Since area changes, the flux changes, and flux changes in time, and time-dependent flux generates current in our loop. Wonderful. Now we need to figure out what will be the direction of this current, and I like to find the direction of current from the very beginning using Lenz's law. So let's think about it. When I move this rod, area bounded by this loop decreases, area decreases, which means that flux decreases, which means that the magnetic field, self-induced magnetic field generated by induced current, should be in the same direction as original one to oppose the change. Since flux decreases, B self-induced should be in the same direction as B external. As B external, this pink B produced by this I node. B self has to be in the same direction as B external. I will use blue to show B self. B self is out. Now, if B self is out, what should be the direction of current? So I put my thumb along the magnetic field. I bend my fingers, and my fingers go in counterclockwise direction to have my thumb out of page. So if B self is out, the current has to be in the counterclockwise direction. Current is in the counterclockwise direction. Now we know the direction of the current, and now we follow the steps to solve this problem to find the magnitude of current. What are the steps? Step number 1, as always, the way we go around the loop. And the way we go around the loop will be counterclockwise direction, because we follow the convention, and convention tells us that we go around the loop in counterclockwise direction, and our thumb shows us direction of ds, which is out. ds, the area vector, is out. dr will be in counterclockwise direction. So first, we are done with the first step when we found the direction of dr. Second step, we need to figure out what is the flux of the magnetic field. By definition, phi is integral b dot ds. We are talking about this external magnetic field. Forget about this b self. We already used it to figure out the direction, but we ignore it when we find the magnitude of induced current. So B, this B that is generated by this current I node, is out of this page. Let me just erase B self. We already used it. B is out of page. ds is out of page. They are parallel to each other. Is B the same at each point of this frame or different? Look at this. B changes. The further we go from this wire, the smaller is the magnetic field. So I cannot take it out of integral. I can simplify this dot product by writing it as B times ds. But now I need to take the integral. I need to integrate this magnetic field. And to do it, we need to introduce a coordinate system. Let me have my y down. And then the magnetic field, what is r? R is now y. I have the magnetic field as mu naught I naught divided by 2 pi. We rename it as y. What is ds? We need to integrate. I cannot write ds as we did before. By the way, I forgot to give you this dimension. This dimension is L as always, and this dimension is changes. So as always, we call this dimension of the frame that changes as x, and then my area will be ds. We understand that we need to integrate along y. We will split this area into these stripes. This dimension is x. This dimension will be dy, because the magnetic field changes in this direction. So my ds is x times dy. And the limits of integration will be from a to b. Okay. Let's take this integral. It will be mu naught I naught, constant, divided by 2 pi x. And then dy over y integral gives me a logarithmic function of b over a. I plug in the limits b and a. Logarithmic function of y, absolute value, b over a, we have positive number. Okay, so this is the flux. Step number 3. Now we take derivative of the flux, d phi dt. What is d phi dt? What changes here with time? X is changing, so it is mu naught I naught divided by 2 pi, logarithmic function b over a, nothing changes with time, and then derivative dx dt, because the length, this length is changing. Okay, so what is dx dt? As we move this rod in, x decreases, so we have negative derivative of x. That's why dx dt is minus v. So I plug it in here. This is minus v. I have mu naught I naught divided by 2 pi, and then logarithmic function b over a, and minus v. That was d phi dt. All we need to do now, we need to write the left-hand side of Faraday's law and bring everything together. So I erase this, and we move to our last step. What is integral E dot dr? I go around the loop in counterclockwise direction. Current is also in counterclockwise direction. So J is in counterclockwise direction. E, electric field, which is rho J, is in counterclockwise direction. So I have dr that is parallel to the electric field, which makes E dot dr positive when I go across both of these resistors. So it will be current I. When I go across this resistor R1, then it will be, again, we go down, current goes down, and we go down. So it will be plus I R2. This is the left-hand side of Faraday's law. And this is equal to minus from Lenz's law. This minus from Lenz's law. And then d phi dt that we already found. So the this d phi dt is equal to minus mu naught I naught over 2 pi, and then logarithmic function b over a and v, minus minus plus, and finally we have our final answer. Let me erase step 1, direction of dr, and we will write magnitude of current. So what will be current? Current I will use pink. Current I will be equal to mu naught I naught over 2 pi v, logarithmic function b over a, divided by R1 plus R2. R1 plus R2. And this current is, this is from A to B, and this current is in counterclockwise direction. So what's important? This time the magnetic field was not constant. It was changing with the coordinates. So it was changing, it was different at each point of this area. And we had to integrate to find the flux of the magnetic field. By the way, just making sure that we understand what's going on, I will put parentheses. So this b over a belongs to this logarithmic function. So we found magnitude, the magnitude of current, and the direction of current generated by this in this circuit.